I've drawn a very simple Turing machine on the board. Okay, so let me tell you about it. It has two states, and then the halting states for error and for accept, for yes. Okay, and it starts in state Q0. If it reads in a pound or space, you immediately reject. If you read in star or 1, you stay in this state and move right. If you read in 0, you move to the other state and move right. Okay. Nowhere is this guy writing anything to the tape. So all it's doing is reading and moving. Okay. Now, if you're in state Q1, if you read in 0, pound, or space, you just you transition to the halting state and accept. Okay. And if you read in 1, you move left. Okay, so you move left and transition to state Q0. Okay, so it's a very simple Turing machine. Exercise. Okay, supposing the tape input is 0, 1. So the start state, it looks like this. So you've got your beacon state star, and the input is 0, 1, and then you've got some blanks. So this is the tape at the beginning. What happens? So I give you a few seconds. I give you 5 seconds so the Turing machine starts by reading in star. Okay. So go. Run this Turing machine on this input, and that's an exercise. Do it. Tell me what happens. Okay, 1, 2, 3, 4, 5. Okay, now I'm coming back. I'm going to tell you what happens. Okay, and hopefully you agree. Okay. So you start on star, so you stay in Q0 and move right. So you move right. Now you read in 0, so you read in 0, you move right. Okay, and you move to state Q1. When you're in state Q1, okay, you're now reading in 1, so you're in state Q1, you're now reading in 1, so you move left. Okay, and transition, you move left and transition to state Q0. But now you're in state Q0 and you're reading in 0. So you move right, you're reading in 0, you move right and transition to Q1. Uh-oh. But now you're back in Q1, reading 1, so you move left and transition to Q0. Uh-oh. Uh-oh. So you see the problem. So we gave our Turing machine a RAM. Okay. In order to be able to access this RAM, we have to give the Turing machine the ability to move. Okay. But with this ability to move has come a very unexpected consequence. Okay. And what is that unexpected consequence? Here's a very simple Turing machine, and it doesn't have to be a complicated Turing machine. Here's a very simple Turing machine that on this input goes into an infinite loop. So an undesirable consequence has arisen. Infinite loop. Okay, so let me take you through the logic. We started with a simple DFA. Okay, it was insufficient. It couldn't solve equality. Then we added stack memory. Insufficient. Couldn't solve repetition and other problems. Okay, so then we said, oh, let's add random access memory, and to be able to access random access memory, you have to be able to move. So now we can solve all kinds of problems. Very powerful. Basically, we can solve anything. Okay, but the fact that we added mobility, the fact that we gave it the ability to move around in its RAM, gives it the ability to just roam around its RAM forever. Roam. It goes right, left, right, left, right, left, right, left, right, left. Okay, infinite loop. So in an attempt to give our machine enough power to solve sufficiently interesting problems, okay, in some sense we have given it, in some sense, too much power. So now it can infinitely loop, and especially if you construct a bad Turing machine. And all of you guys have experienced this. You write a piece of code. What that means is you built a Turing machine. You write a piece of code, and then you run it, and it never stops. And you're sitting there wondering, whoo, is it going to stop? Or is there a problem? And the issue here is that when you have the possibility of an infinite loop, it throws everything to the dogs. Okay? Because it's possible that your program will stop, but you just haven't waited long enough. So you wait that extra 1 second. Okay? And then it still hasn't stopped. So you wait that extra 1 minute, and it still hasn't stopped. So you wait that extra 1 minute. When do you know to terminate? When do you know it's gone into an infinite loop? Or that it's, going to stop eventually? Okay? So the ability for Turing machines to infinite loop is a big, big disaster. Okay? So now, let us define some things. Okay? So I've called this machine M. Okay? And let's call this input W. Okay? So when M operates on the input W, one of three things can happen. And this wasn't possible with the DFA. So when M operates on W. Now, with the DFA, you either say yes or no. Okay? And the computation is, terminated. It's forced to terminate when you're done reading the input. Here, there's no reading of the input. You just roam around your RAM, and at some point you enter one of your halting states and deliver a verdict. Well, the issue occurs when you don't enter a halting state, like here. You roam around forever. Okay? So when the machine M operates on the input W, it can either halt and say yes. So halt and say yes. It can halt and say no. Okay. Or, as this example illustrates, it can go into an infinite loop. So, infinite loop. No, halt. Infinite loop. This is the disaster child. Okay. Because that leaves us forever wondering, are you going to halt? Should I wait a little more? Or are you in an infinite loop and I should hit Control C? Okay. And so this leads us to the definition of what problem does a given Turing machine solve? So given the possibility of infinite loop, what problem does a Turing machine M solve? Okay. So we say that the problem solved by a Turing machine, and we call that the language solved by the Turing machine, is the set of strings for which the Turing machine halts and says yes. Equals the set of strings for which the Turing machine halts and says yes. Okay. So let's say you have this language. So you have this language L for a Turing machine M. So you could ask, what is the language of this Turing machine? So what is the set of strings for which it halts and says yes? So if you have a string in the language of the Turing machine, it means that it halts and says yes. If you have a string that is not in the language of the Turing machine, okay, it means that it either halts and says no, or it infinite loops. And we say that the language L is recognized by the Turing machine M. Language L is recognized by Turing machine M. And we also say that M is a recognizer for L. Now, so when you have a Turing machine that is a recognizer for L, you are in a dilemma. Because you're running your Turing machine on your input W. And let us say that the input W is in L of M. But it's going to take 17 years for the machine to stop and output yes. So you're waiting for 16 years, 16.9 years, 16.99 years, you're waiting, and at some point you have to say, you know what? I think this thing has gone into an infinite loop, so that W is not in L of M. Okay? And so this infinite loop option that has appeared creates major havoc for programming. Okay? And so what we have ultimately decided is that, while yes, it's nice to have Turing machines and it's nice to know which strings the Turing machine halts on, okay, those are not much use as computer programs that solve problems. So recognizers, which could in principle, or which have the possibility of going into an infinite loop, recognizers, okay, are of no practical use. They are nice, okay, they tell us about theoretical properties of machines and Turing machines, and we could ask what languages are recognized by Turing machines, but they are of no use in practice. Okay. So in practice, we are only interested in Turing machines that do not infinite loop. So practice. And so we're going to build a theory that's relevant to practice. Okay, so practice. Turing machines or computer programs, Turing machines must halt. What use is a program that doesn't halt? What use is a computer that doesn't halt? Okay, so we don't consider a Turing machine with the possibility of infinite looping as a valid, computing machine. Okay, and so in addition to recognizers, we sort of acknowledge the existence of another kind of Turing machine, the kind that we are interested in. Okay, and that kind of Turing machine is the one that cannot infinite loop. Okay, so if we require that the Turing machine does not infinite loop, then for a W in the language, it halts and says yes, and for a W that's not in the language, it must halt and say no. Okay, and so such a Turing machine, which must always halt, we call it a decider. So we say that the language L is decided by the Turing machine M, and we say that M is a decider for the language L. So recognizers may infinite loop. Deciders must always halt. Always halt. Okay. So we have identified now in this very powerful model of computing the existence of two types of machines. Those, that are interesting in theory, but we don't care for them in practice, which are recognizers which can infinitely loop. And what we care about in practice are deciders which must always halt on any input. And if you have a decider, then you can wait 17 years and you know it's going to halt, so you'll wait another 17 years. You'll keep waiting until it gives you the decision. Okay? But if you had a recognizer, you wouldn't be able to distinguish between an input that's just taking a long time to say yes or no, and an input that's caused it to go into an infinite loop. So it's easy for us to accept that, Turing machines that can go into infinite loops are a no-no. Turing machines that must always halt, that's what we want. Those are called deciders. Okay? And so now I'll tell you a little bit, I'll just in one line tell you what is the Church-Turing thesis. The Church-Turing thesis. It's nothing special. It's just these guys are, famous guys. The Church-Turing thesis says that our intuitive notion of an algorithm, what we call an algorithm, is a Turing machine that always halts. An algorithm is a decider. Okay, and so that's the Church-Turing thesis, that anything that you can consider an algorithm is equivalent to a Turing machine that halts, i.e. a Turing machine that's a decider. Okay. And so when we say that an algorithm solves a problem, that algorithm must always halt. Okay. And it can be represented by a Turing machine. It can be implemented by a Turing machine. Okay. And this thesis has withstood the test of time. So anything that we call an algorithm, you can implement a Turing machine to solve. And so therefore, the Turing machine is the model of computing that captures the notion of an algorithm. Turing machines that always halt. Okay? And so that's where we are right now. We have awesome power. We can do all kinds of things, including infinite loop. And so we exclude the infinite loop, which is recognizers, and we get to what are called deciders, and deciders are what we call algorithms. So if you're walking down the street, and someone says, hey man, you're a computer science guy, tell me what's an algorithm? You say, it's a Turing machine that halts. It's a decider. What's a computing problem? It's a language. It's a set of finite binary strings. So a computing problem is a set of finite binary strings. An algorithm to solve the computing problem is a Turing machine that always halts, and if you give it a string that is in the language, it says yes, and if you give it a string that is not in the language, it says no. It halts and says no. So that's what it means to be a computing problem, and that's what it means to solve the computing problem. Produce a Turing machine that's a decider that always halts to solve the problem. Okay, now, we're going to leave it at that. I'm going to come back and discuss just one more minor detail, which is going to be useful later. Okay, so let me erase